Hi everyone, I'm Chuck McLennan for Buick Know-how. This month's program focuses on vibration diagnosis. The Know-how Reference Manual has all of the information about vibration necessary to diagnose vibration in any Buick. While in this video, we're going to concentrate on vibration specific in 94 to 96 centuries. I'm sure you've heard about the 25 Hz Riviera body structure. The Century is an older design, and the body structure is about 15 Hz, which in itself isn't bad. Unfortunately, the 3100 engine, the tires, and the rear suspension components can start vibrating at 15 Hz when the car reaches 70 to 74 miles per hour. When one component vibrates, it can cause another unrelated component to start vibrating too. This is called resonance or resonant frequency. The Century body structure has a resonant frequency of 15 Hz. When the engine, tires, and rear suspension create a 15 Hz vibration, the Century body structure starts resonating because it's naturally tuned to the same frequency. The important thought here is that the body structure starts to vibrate by itself. The only theory we need to talk about is how the vibration gets from the tires to the instrument panel. So, let's follow its trail. The vibration begins at a source, travels along a path, and excites a responder. What do I mean by that? Well, the source is the actual component or system producing vibration. As vibration feeds into the body, it travels along a path. For the most part, the body structure is considered the path. The responder is the part of the vehicle that reacts or responds to vibration. This is usually an unrelated part or system. The responder is the part of the car that the customer sees, hears, or feels. In the Century, this is usually a vibrating instrument panel and steering column. When driving between 70 and 74 miles per hour, the Century arrives at the point where the engine, rear tires, and rear suspension are all generating the same vibration. Because the Century body structure is sensitive to this vibration, a resonant vibration may begin, causing the instrument panel to shake. In the South, roads are surfaced with a dark pitch asphalt that provides a very smooth surface. The vibration occurs with nothing to interrupt or break up a resonant vibration. Remember, this doesn't happen to every Century, and it doesn't happen nationwide. In most of the northern states, the interstates are concrete with tar strip construction. Concrete surfaces create tire noise that is not in the 15 Hz range. Tires are not a vibration source because the tar strips break up any vibration patterns. In the Southwest, asphalt roads usually have a heavier gravel content that creates tire noise. This tire noise usually prevents the concern. But if the tire and wheel assemblies are out of specification, you could see the instrument panel vibrate. In 1994, Buick began using the 3100 V6 engine. The 3100 produces a 15 Hz vibration at the 70 to 74 mile per hour speed range. In addition, the catalytic converter had to be closer to the engine to meet emission standards. When the converter was moved, a heat shield brace was eliminated, and the sensitivity of the body became more receptive to engine, rear suspension, and rear tire vibration. If you get a car with a vibration at speeds other than 70 to 74 miles per hour, repair those vibrations first. If you only get a 70 to 74 mile per hour vibration, follow this sequence of repairs. Always start with a critical visual inspection of each tire. Make sure the tread is evenly worn with no signs of cupping. Other tire problems to look for include abnormal wear along the outer edges of the tread. This indicates insufficient tire pressure. Worn tread in the center of the tire suggests excessive tire pressure. Also, make sure that the tread is not abnormally worn from aggressive cornering or excessive camber. Replace any tire that shows abnormal wear. After you make sure the tires are in good condition, mark the rim and a stud so that each wheel can be reinstalled in the exact location. Then balance each tire and wheel assembly. Make sure you calibrate the balancer. This is very important. If the vibration is due to a rear tire and you only balance that tire, the problem may reappear when the tires are rotated. To prevent an instant comeback, balance all 4 tires and wheel assemblies. Remove mud, grease, and dirt from the rim because they can affect the balancer's readings. Make sure the center pilot hole is clean. You need to have good contact between the rim and the cone. Remove all balance weights. Then, remove all stones from the tread. Then, spin the tire up. And install the required balance weights. When balancing aluminum wheels, use a flange plate adapter to locate to the stud holes in the wheel. If you have one, an on-car wheel balancing spinner can be used to spin one wheel at a time. By sitting in the driver's seat, you can easily tell which corner of the car is causing vibration. Many times a simple wheel balance is enough to stop the instrument panel vibration. If a wheel balancing job didn't solve the concern, you'll have to measure tire runout. Now, to some technicians, this may seem to be too basic, but to repair this vibration, these measurements must be made, and they must be made carefully. Radial runout means the tire rotates in an oval pattern. Lateral runout means the tire wobbles side to side. Wrap tape around the circumference of the center tread. Use dial indicator J8001-3 with a magnetic mount. Be sure to use roller tip J23672. Place the dial indicator wheel against the tape. Slowly rotate the tire to find the lowest spot on the tire. Zero out the dial indicator gauge. Slowly rotate the tire again. The highest reading indicates the radial runout. The specification for tire radial runout is 60 thousandths of an inch. Check lateral tire runout next. Place the dial indicator wheel against the sidewall near the tread edge. Again, rotate the tire to find the lowest spot. Zero the gauge and rotate the tire again. The highest reading indicates lateral runout. Note these readings. The specification for tire lateral runout must be within 60 thousandths of an inch. Repeat this procedure on the opposite side of the tire, but don't condemn the tire until you check the wheel readings. So, perform an on-car wheel lateral runout check. Place the dial indicator wheel against the outer edge of the rim bead. Find the wheel's lowest point. Ignore any readings caused by paint runs or welds. Zero out the dial indicator gauge. Rotate the wheel. The highest reading indicates wheel lateral runout. Repeat on the opposite side of the rim. Specification for lateral runout are 45 thousandths of an inch for steel wheels and 30 thousandths of an inch for aluminum wheels. Next, check the wheel radial runout. Set the dial indicator's wheel against the underside of the rim, near the bead. This reading tells you if the rim is rotating off-center. Again, find the low spot, zero the gauge, and get the highest reading. Repeat on the opposite side of the rim. Specification for wheel radial runout are 40 thousandths of an inch for steel wheels and 30 thousandths of an inch for aluminum wheels. If the car seems to be very sensitive to wheel vibrations and runout readings are within specification but are very close to the outer edge of the specification, consider trying a replacement wheel. Be sure to measure radial and lateral runout on the new wheel first. Hub runout is another vibration source that can be hard to diagnose. It's best described as a rhythmic moaning or droning noise. You can hear this noise even if the tire and wheel assembly is perfectly round and balanced. Front hub runout is not much of a concern. The rear hubs, however, can create a twitchy or jumpy feel to the rear suspension. Perform a hub runout test. Mark the wheel and a stud so the wheel can be placed back on the original studs. Remove the wheel and reinstall it 2 stud holes away from its original location. Torque the lug nuts to 100 pound-feet. Measure wheel radial runout again. With the wheel in a different position, hub runout can be easily detected. Determine the difference between the 2 radial runout readings. If the difference is more than 5/1000ths of an inch, replace the hub. If you have any doubt, check wheel runout on the tire balancer. This hub was sent to Buick Service Engineering from Roger Dean Buick in Fort Pierce, Florida. The guys at Roger Dean found a hub runout of 45/1000ths of an inch. The new hub fixed the vibration. Some Centuries are more sensitive to tire and wheel assembly vibrations, so check the balance of the rear brake drums. Set the diameter to 11 inches and the width to 3 inches. Be sure that the machine can measure to within 1/10 of an ounce. If your machine has a static setting, the balancer turns slower. If the drum is out of balance more than 1/4 to 1/2 ounce, replace it. While the drum is turning, look closely at it. If the drum looks like it's rotating off-center at all, replace it. Once the tires, wheels, hubs, and brake drums are balanced, measured, and any problems corrected, drive the car again. If the concern still exists, the floor pan is continuing to be a vibration path. All you have to do is alter the sensitivity of the floor pan by attaching 2 steel braces to existing holes in the floor pan. The braces change the floor pan sensitivity and stop vibrations before they travel to the instrument panel. This set was manufactured by a fabricating shop. But I'm going to make a set from plain stock. The braces are different, but they install in existing floor pan bracket flange holes. It is not necessary to drill holes in the floor pan. To make the front brace, mark the bends from the dimensions in the manual. Clamp the steel in a vise at the second mark. Heat the steel and make the first bend. When you're finished, the brace should look like this. Then, mark and drill a 7/16" hole and a 7/16" slotted hole. Now for the hoop brace. Form the steel around a brake shoe clamped in a vise. Heat the steel red hot and bend around the brake shoe. The finished diameter should be about 10½ inches. Measure and mark for the slotted hole. Drill 2 holes and file to form the slotted hole. Paint the brace with zinc chromate primer or equivalent. Bolt the front brace to the floor at the toe pan. Slide the nuts into these brackets and install the bolts. Torque the bolt to 30 pounds-feet. The hoop brace fits over the rear of the catalytic converter. Install the brace into the punched holes in these floor pan flanges. Insert the nuts upside down. Torque these bolts to 30 pounds-feet as well. Make sure the brace does not contact the converter heat shield, avoiding a buzzing concern. Okay, you've done everything so far. You've installed braces, but that didn't get rid of the vibration. Now it's time to install new tires. Buick service engineers know that tires for this car have to be able to cushion or soak up as much road shock as possible. For this concern on the Century, Buick selected the Michelin XZ4. The XZ4 does the best job of isolating vibrations. Plus, the XZ4 has the ability to stay rounder. This really helps reduce tire runout. Now you're back from a test drive and you've hit the wall. You've tried it all. Checked tire condition, balanced tires and drums, measured wheel and hub runout. You've made and installed floor braces, mounted new tires, and you still have a vibration. As a last resort, to satisfy your customer, remove the XZ4s and reinstall them on a set of new aluminum wheels. Eliminating vibration is always a tricky job, especially in this case. With all of this new information, you should be able to identify and repair any 70 to 74 mile per hour instrument panel vibration. See you next time.